Hi, everyone. I'm very excited for today's session. We have Karine as our presenter. We also have Denise and I as host and co-host. So please, if you have any questions, don't doubt to post them in our QA box at the bottom of your Zoom screen. We will be answering those questions at the end of the webinar. And I think today is going to be a very interesting session, both for database admins and developers. So let's go ahead and get started. Can you go to the next slide, please? Thank you, Karine. So if you want to see any previous Spatial Ask Some sessions, or you want to sign up for future ones, you can go ahead and follow that link. We will be posting that link in the chat for everyone to have access to that link. And next slide, please, Karine. Thank you. And today, Karine is going to cover how to check spatial in your database instance, tips and tricks for working with vector data, and other useful information. So I'm going to go ahead and hand it on to Karine. Thank you so much for presenting today, Karine.
Thanks a lot, Ramu. Okay, so let's get started with the technical stuff. So the first thing I want to talk about is the Oracle Spatial software component as part of the Oracle database. And you probably are familiar that Oracle Spatial is part of every edition of the Oracle database. So make sure you have it properly installed. Then you can use it to its full extension. In order to make sure that it works properly, we recommend you that you check whether you have the latest Spatial bundle patch for the Oracle database installed. And in order to check this, I recommend you to use the Oracle support note. You can see the ID here. It's 2514624.1. This is the master node. And there you can find all the information about Oracle Spatial, the different versions, and which bundle patches are available for which version and what the bundle patches contain. So I recommend you to flag this document as one of your favorites if you have to deal with spatial data on a regular basis. So in Oracle 12c and 19c, the spatial bundle patches are separate from the database periodic safety updates and database release updates. And what you find in the document, since it's a live document maintained by Oracle support, you find all the database release update specific recommended patches which you need to apply. You find information when a new DBRU will be out, and also if spatial patches are superseded. So check the README for details for a specific bundle patch, in order also to find information about the things that had been fixed, or things that are new to a certain bundle patch. And here, just for the last two entries, since we are with the Oracle database version 19c, we have 1920 is a current version. So the spatial patch bundle has a number which is displayed here. So make sure that the software is properly installed with all the necessary spatial bundle patches. If you want to avoid bothering yourself with patching, upgrading, and those kind of things, I recommend you to consider the Oracle Autonomous Database, which is a fully managed autonomous service which we provide in the Oracle Cloud. And as you can see here, for one of my database instances, you see here that there are patched every week. So we have a weekly cadence to patch the autonomous database. And there is nothing you need to do about it. Also with regard to backups, they are automatically done. So if you want to avoid maintenance tasks that are rather boring than exciting, just have a look at the Oracle Cloud and the autonomous database service there. Okay, along with the spatial features in the Oracle database, which we call the spatial component or SDO, spatial data objects, there are certain database objects installed in order to use spatial functions properly. And you can check whether the spatial software component is properly installed. And if you do that check and you discover invalid spatial objects in the database, then you should do something about it. Why? Typically, an invalid or invalid spatial objects lead to an invalid spatial component in the DBA registry, and this actually causes typically undesired errors. So in order to avoid spending time and especially nerve-wracking time, you should make sure that all the spatial software or the spatial software component and all database objects needed for this is valid. How do you do that? Let's have a look here. So in order, dependent on whether you are in a container database or in a single instance database, you need to check whether the spatial component is properly registered, and the statement you will be using for this is that one here: select component status from the DBA registry, and the component name is SDO for spatial data object. And there is another statement to check whether there are invalid spatial objects in the database. And since you should be familiar with the fact that the owner of all spatial data objects is called MDSys, MD for multidimensional, you need to check the status of all the objects belonging to that database owner. And if there are any objects listed as invalid, then as I said before, you should do something about it. And for that, you can also consider having a look at the document which is listed down here in my Oracle support to get proper instructions on how to handle the situation. Okay, so this is the part that is most interesting for database administrators and also for DevOps engineers. The next topics are especially interesting for those developing applications using spatial data, administering spatial data, or working with spatial data in general. And this applies for developers, analysts, DevOps engineers. So you all should get something away from the tips and tricks I'm going to share about vector data. I'm focusing on vector data because the last session, or one of the last sessions we did, we talked about raster data. So you got a lot of tricks working with raster data already there. And this time I'm focusing on working with vector data. One thing I highly recommend you to check is the fact that we have a feature in the Oracle database which is called Spatial Vector Acceleration, or it's also known as Vector Performance Accelerator. And this is enabled using a database initialization parameter, and you can set it on or set it off or enable or disable it. Typically for versions until 19C, the default is false, so it is disabled. But I highly recommend to enable it because you will gain typically performance optimizations. So running spatial queries, spatial operations that require a spatial index typically run much faster than without having the spatial vector acceleration enabled. And it's especially interesting for those queries that are have as a query window a geometry with a lot of vertices. So here we call it high vertex count. So imagine coastlines of Norway, for example, or Sweden, or time zone polygons. Those have a lot of vertices belonging to the geometry. And this could actually take some time in using those query windows for spatial queries. And the operators you will see significant performance typically are related to topological relationships, to spatial aggregations, and other operators as well. And for the spatial, the topological relationships, we will be seeing in a few seconds also examples using those covered by, covers, touch, masking operators. So here is how you can check whether the vector performance accelerator is enabled. So you show the database parameter, and if you find that it's set to false, then you can enable it via assigning the value true. And you can either do it as a database user with sysdba privileges, but don't forget to also use the clause scope equal both in order to make sure that once you restart your database, the setting still applies. And for those who are not granted with sysdba privileges, but with alter session privileges, so maybe as a developer, you get the alter session privilege granted, then you can set alter session, set spatial vector acceleration true as well as a session parameter. Of course, if the session terminates, then it's set to the previous or the default value, which is, as I said, for 19C still false. Okay, and I promised that you will be seeing typically performance improvements, and I've already taken the result of the demo I'm going to show and put it onto the slide here. And there are 3 test cases I'm going to show you. One is aggregate union, so spatial aggregation with the vector performance accelerator enabled or disabled. And what you see here is we have in the first test case, we have a factor of roughly 10 comparing not using VPA versus using VPA. For the topological relationships using touch and covered by, we have 2.5, the factor of 2.5 improvement. And here with SDO touch alone, we also have roughly a factor of 10. And I'm going to switch over to my demo environment. And what I'm going to show is, actually I wanted to just get started with a brief intro, what you will be seeing live here. So I'm going to create a test table with the results of my test case, and I'm going to measure the start time, end time, and calculate the execution time. And here are the test cases I'm going to run. One time with without VPA, and the other time with VPA. And here you can see that I'm going to query a data set I've taken from a public website where you can download a country or the administrative boundaries of most of the countries of this world. And I've picked a few countries to show these use cases. And here I'm going to query the level 2 admin boundaries for Finland using spatial vector acceleration, either disabled or enabled. And when running the second use case, I'm sorry, let me check that. Yeah, I just wanted to show you these things here. And let me just check whether I wanted to run these already. Yep, let me just run this also. Okay, so we run, oops, sorry. So let me just, so this is the script, 02C tests VPA. And here I'm going to run this one. Oh, okay, my connection closer was too long open. Let me just restart. Ask Tom. Sorry for that. Okay, so here you can see that here is my data set. So in order to get proper results, I told to flush the shared pool. I told the database to flush a shared pool. Then I disabled spatial vector acceleration since it's enabled for my instance. And then I'm going to run the scripts that are there. And the test scripts will run for a while, but you should already see that having the spatial vector acceleration set to true will cause much faster execution times. So let this running in the background, and we can look back at it once we come back to the demo for the next use case. Okay. One other very important thing is that you make sure to validate your spatial data. Spatial data, spatial vector data are standardized. There is a joint there are joint forces by the Open Geospatial Consortium and the ISO to define a standard for geometry definition and validation. And we should make sure that all the vector data stored in the database are standard-based, meaning that they shouldn't have any repeated consecutive points in a line or polygon, or any self-crossing polygons, or the wrong orientations in polygon rings. And also we should make sure that we, for 3D vector data, we also have reference system assigned that is a 3D coordinate reference system. This is a new test which we introduced or we enforced as of version 90C. So probably you won't, or if you have 19C and you will get an error message related to this test. And if you compare it to a 12C instance, you won't find it in 12C, but it's now checked as of 19C. So make sure you validate your data. Typically, we recommend that you validate the data as soon as you either create them or you load them into the database. And there is a PureSQL package containing two functions for validating the geometries. The first one is validate geometry with context, and the second is validate layer with context. And I'm going to show how you can use those ones as well. If you see any invalid geometries, then you should make sure you fix those before performing any spatial operations. If you perform spatial operations, you might get unexpected results or strange results you're wondering about. So it's always a best practice to do the validation as soon as possible. So let me get back to my demo environment. So here you see the result of the previous test with the different test cases, and vector performance acceleration enabled the test case, and the numbers, they are similar to what you have seen before in the slide. Okay, so let me use my next script. Just need to check that. Maybe I'm going to show it to you first. Let's close those ones. So what I'm going to do is check invalid geometries here. So I'm also creating a table where I put all the arrows in it. And then there is a script my colleague Albert Godefroy provided in his spatial workshop, which fetches all tables with geometry tables, then iterates over all the tables and the SDO geometry columns, and validates the entries in those tables. And this is done by this script here. So here he actually checks for all the tables having SDO geometry columns. Then he is checking the spatial metadata stored in the view user SDO geom metadata in order to fetch the tolerance stored for a table and the spatial column. And then using the tolerance, the script will iterate over all the tables and the geometries in those tables and validates those using the tolerance given in the user SDO geometry metadata. This script might take quite a while since it iterates over all the spatial tables and all spatial columns. There is a fast track, actually, I want to show you, which is this one. And here we have a script that does the table creation and fetching the invalid geometries at the same time, and putting the geometry errors for one table into that geometry errors table. And let me do that one. Okay. And here we can see that it's very fast operation. You can use parallel to do the validation in parallel, depending on your underlying hardware environment, storage of the data, and so those kind of things. A CPU, you should either profit more or less from parallel queries and parallel operations. But here you see that we've found for the table the admin level boundaries for India of level 3. We have one geometry that is not valid. And what you see here is that we have a tolerance defined according to what's mentioned in the SDO metadata. You might see the effect that using a different tolerance, a smaller one, that you won't see, or you will get a validate true. This is because with a smaller tolerance, there's also a smaller difference between two vertices, and having two vertices which are close to each other, which is actually the case for this error message here, then you might see the error going away if you use a smaller tolerance, and then having this tolerance, the vertices are actually apart enough to return a valid geometry. So these are things where how you can validate your geometries. And now the interesting fact is how you can handle the situation you have some invalid geometries. So let's see here for the admin boundaries for France, India, and also Finland. You will find invalid geometries, which I haven't fixed yet, but this is a topic of the next slide, how you can fix those. One method to fix invalid geometries using Oracle spatial features is to rectify a geometry. And this is part of the SDO util package. And what the rectify geometry function does is it validates the geometry first, and if it's correct, the geometry remains unchanged. If it detects one of the known errors, it tries to correct them. There are certain cases where you will find an uncorrectable error, then you will see an exception coming up. And maybe this process, these process steps are repeated depending on whether there are some underlying errors once you have rectified a geometry, and it turns out that even the rectified geometry has a different error, then of course you need to check it again and apply the methods to make the geometry valid. So you will see that not all of the invalid geometries can be fixed, but we were able to fix quite a lot of those over the past years. I've worked with customers and partners. This was one of the methods that is best practice to be used. Okay, so how does this work? So here is this rectify geometry. So first we are going to validate the geometry. This is a function called for validating the geometry. And then we call rectify geometry via the SDO util package, also using the tolerance registered for that spatial table and column. And then you can display the result of it. If you want to do it yourself, this script or pure SQL script is actually also posted on in a blog post written by Hans Fiemann. So it's called Validating and Rectifying Spatial Data in the Oracle Database. And here is the link. I highly recommend to read that link to get also some better understanding of the whole issue with invalid geometries. Okay, we have something new, which is also validating the coordinate system. I mentioned before that since 19C, we also validate that, or we check that for 3D data, there should be a 3D coordinate system used. And in general, we also have a function to validate all the coordinate systems registered in the Oracle database. And this function, SDO underscore CS, CS for coordinate system, and validate underscore WKT, and WKT is short for well-known text, a standard format for geometry data. And this is how we can validate also the coordinate systems registered in the Oracle database. So let me just go back to that one. So I'm just going to show you how the script is. So it's actually similar to what you have seen before the script. So I'm going to create an error table to store the error messages, so I can later on check the error messages and work on the corrections for it. And here is actually the function call, which returns the status information. I'm going to check the status and extract the details from the error message to get a better understanding of what's actually wrong with that coordinate system. Okay. Another topic that also refers to 3D geometries. If you store a 3D geometry, or very often we have customers storing geometries or vector data as 3D geometries, even though all the third parameters, the Z value, typically the height, are set to 0. So this can cause some problems. Doesn't have to, but in either way, having all the values, Z values set to 0, makes your geometry larger than it should be, because it uses a third more space to store the third parameter for a vertex, which is actually not required. And also when loading the data, you also have to load the third value into memory, which is actually not required and waste of resources. So what we do recommend is if you don't require the Z value, then you can turn the 3D geometry stored as GD type 3 something. You can transform that one into a 2D geometry. And this is what you can do in this solution. So find out which 3D geometries have Z0 value, Z value 0, and then check whether you can actually transform those into 2D geometries. This, of course, depends on the, or it should be discussed with the application owners and maybe also the data providers. But if you can correct those, then we recommend to do that exactly. So the first thing then would be to drop the spatial index on the column if one exists, then convert the existing 3D geometries to a 2D geometry. There is a function you can use as part of spatial, which is sdo_cs dot make underscore 2D. So it makes a 2D geometry from 3D geometry, and then you can recreate the spatial index, which has as default, takes as default the 2 dimensions if you don't specify it differently. So this is the way you can actually handle this situation. Okay. One very interesting topic is how you can work with large point data sets. If you want to optimize the storage, how you store point data on your file system, then there are options. One of the options we call is we call it attribute clustering. Attribute clustering is actually a table directive. So you have a clause for when you create the table, which directs the table creation to use this attribute clustering, and you also define the columns which will be used for clustering. You should make sure that for loading then the data into that table, you use only direct path insert operations. And there are 2 types of attribute clustering. The default one is linear ordering, which actually takes the columns defined and puts them in the specified order, or it creates clusters the data in the defined order. And there's a second method I'm going to show you in a couple of seconds that takes all the columns specified for attribute clustering and turns them into one-dimensional value and applies that one to create a specific order of how these data are stored physically. And you can see here that it's actually the shape for how the data are stored is that shape storage optimization. Attribute clustering, also we use it for point data. It's not specific to spatial data, so you can use it for other tables and columns as well. In the case of point data, we need to make sure that we don't have the point stored as geometry, because attribute clustering cannot deal with object data types, and geometry is an object type. So instead of storing the point as geometry, we store the coordinate values, either 2 or maybe 3, if you have a 3-dimension, 3D point, then you store those values as numbers. And in order to make sure that you can still use the spatial functions after storing the data, you create a function-based spatial index. And I'm going to show that as well. So assume you have your point data as longitude and latitude value, then you add this clause clustering by interleaved order, longitude, latitude, yes, on load to that table. Or you can also add the capture time, for example, also to, or you can include it in the parameters list. I'm going to talk a little later about lines and polygons, which are typically have undefined number of vertices, so we can't use it the same way as points, which have only either 2 or 3 values. So for lines and polygons, we need to do it differently. For that, we use a function called linear key, which is part of the PSQL package linear st_util. And let me go back to the demo case. So here is what I'm going to do with cluster points. So I'm going to create a table with 1 million random points. This has the capture time, longitude, and latitude value. And then I create it once without the clause and once using the clause, which is this one here. And then we can load the data into that table and use it afterwards. So you will see that it takes a little longer to store the data in the cluster table. Let me just start that one as well. So it's 1,4 cluster points. Oops, sorry, was still again too long talking. Fortunately, the connection closes in between if I'm not refreshing it. But okay. So here you see that we can. It's quite fast to create that table with 1 million points. So here it took 6 seconds to run it, and here let's do it for the other table with the cluster table, and it takes also just a couple of seconds longer to create a cluster table and insert the data there. Okay, so it took 11 seconds rather than 7 to store the data in that table. Okay, so this cluster function is about optimizing this how point data are stored on the physical device in order to make sure that they can fetch as fast as possible. The closer the points are, the nearer they are stored together, and therefore we assure that we don't have to fetch that many data and database blocks into memory in order to do a spatial query. Okay. So I told you before, when storing point data or also lines defined by just a starting point and an end point, or an optimized rectangle which has a point in the upper left corner and another point in the lower left corner and one in the upper right corner. This is what we call an optimized rectangle. As soon as we have these kind of geometries, we can store the coordinate values directly as number values, and then we have a need to create a spatial index based on functions. And I'm going to show you a function that creates from x and y values or longitude and latitude values the geometry for a point, and then we populate the function in the user geometry metadata rather than just specifying the table name and column in order to make sure that the spatial queries run properly. We can also use for point data, an optimized index, which is called CB3 index. It's an index which is works especially well for point data or streamed point data, so where we have a high volume of data manipulation operations. And here the index creation is much faster than without specifying CB3. So what you do first is you create the function, and here we have a function creating a point geometry with a specified coordinate system. It's WGS 84, which has the SRID 4326. Then we register the spatial metadata using that spatial function, function to create the point. Then we create the spatial index specifying the function, here get point, and index type is point, and here we also specify that we want to have a CB3 index via assigning the value true. And then using this function-based index is actually the same way as we do it with the column itself. And this, let me just briefly show it. Oops. So here we have the function. Then we have this spatial, the metadata registered, then the spatial index created, and then having these queries using the spatial index running. And let's do it. So it first creates the function, then it creates the index. So here we have this table with 1 million rows for points. And now we are creating the point index of the spatial index. And now we can query the data. And as you can see here, for an any interact query, using that function, querying the data against the query window defined for a part of Europe, this returns in a fraction of a second. Also, as do any interact using. So, do I? Oh, it's actually, well, it seems to be the same query. I'm sorry for that. I thought it's different. Okay. Now I see. I see the difference. Okay. So here we have the query window defined for these coordinates. So as I said, it's an optimized rectangle with just 4 values, coordinate values. The lower left corner of the rectangle and the upper right. So this is a part of Europe, and here is a bigger part of Europe, taking also fraction of a second only. And here, as a second parameter, we select the geometry from the admin boundaries from France, in which 11.0 is actually the whole of France, and query the points against the whole of France. And you can see here that we've queried 120,000 points in 2 seconds. Okay. So these are actually the demos I wanted to show you in order of the time. Looking at the time, I'm going to skip any further demos, but I also want to mention a few more things. One very important thing is partitioning, and partitioning is especially interesting for the fact that it makes manageability of data easier, loading data, aging older data out. This is much easier when you partition your data, especially when you use a temporal partitioning, where you have as a partitioning key either a date or timestamp column. Then you can use the partitions to query against a time window, and everything that is outside of the time window is not looked at. Or you can say everything that is older than a specified date you just want to delete or move to a different storage, then you can just move the partition or drop the partition, which is a much faster operation than deleting data from a table. In terms of performance, typically using partitioning should also lead to better performance when you query data. Just check it out yourself. Make the tests with your own data and verify whether partitioning would help you and also gaining performance, a better performance. There are many more options how you partition your data. One is, let's say, feature type partitioning. Typically, geometry data have a feature type assigned. For instance, in the utilities area, you have feature types like transformers, utility poles, stations, whatsoever, and you can use those feature types in as lists to be considered for partitioning. But as you can see here, there are many strategies you can apply for partitioning your data: range, hash, list, interval, or reference partitioning. Or you can use two different columns to have the composite partitioning also applied to it. And having your spatial indices or indexes also partitioned, locally partitioned, is typically very effective for performance as well. Okay, you have seen before that I've briefly touched on parallel operations when loading data, creating indices, or creating table as select, or insert append operations, where you can specify that the operation should be executed in parallel. And you can define the degree of parallelism by using or specifying the value here. And my colleague Dan presented a very interesting example for a railway company where they wanted to track all the GPS locations and checked which whether they are co-located with tracks, on which track the train actually was running. And here, in this example, they stored all the GPS positions for the train as they moved along over time and over space, and then they made sure that they can find the closest track for each of the GPS positions to say, okay, this track at this point in time was on that track. And here is how he did it. And there are a few things more to tell about, but for that, I would recommend you check his presentation. I'm just showing this part of the solution here. So he created a table also in parallel. with no logging specified, and then they find the measure between the tracks and the trained GPS positions, and compare those using the SDOGNN, the nearest neighbor operator of the database, to find the closest track. And one last thing, I think it is the last thing, I'm not 100% sure. Yeah, simplifying vector data. Typically, when you have vector data or geometries with a large number of vertices, for visualization, this can take some time to store, to fetch the whole geometry and to display the geometry in your application. To gain a better performance, if you are focusing on faster visualizations, there is the option to reduce the number of vertices in a geometry. This results typically in less accurate geometries, but especially if you look at business intelligence applications where you want to aggregate data and visualize data, this is not that much of a problem. So it's recommended way to simplify your geometries when used in business intelligence dashboards or whatsoever. There are two methods provided by the Oracle database: SDO_UTIL simplify, which uses the Douglas-Peuker algorithm, and SDO_UTIL VW, which uses a different algorithm. You need to give some parameters. One of the parameters is a so-called threshold, which here needs to be a positive value, and the bigger the value is, the more intermediate vertices will be removed. And here for the second algorithm, you have a percentage to be specified. So you have a value between 0 and 100. And this is how you would do the simplification. And here I've put both calls and methods in one statement: simplifying using the Douglas-Peuker algorithm, and simplify VW, the second one. And the result of that one is actually for the geometries in the France admin boundaries, the original number of vertices is the one in the second column. The vertices returned by the first algorithms are here, using the threshold value 60, and the same threshold value 60 for the second parameter reduces the number significantly because it's the percentage value. Okay, and this is also something I will leave to the recommended presentation by Dan Geringer. I'm going to provide the link for. Okay, awesome. So you've learned a lot about spatial using and working with vector data. Hopefully you can get something away from it. And if you need more, just let us know.
Definitely. Thank you, Karin. In here, we have a couple of links with resources like general information, Oracle Live Labs. That is a great place for you to get started with Spatial if you don't have a lot of knowledge on it and you want to get started really easily. It's a great way to start. We have links to blogs, our YouTube channel with a couple of videos on demonstrations, previous presentations. We have LinkedIn, where we use to update people on what's new in Spatial and Graph, as well as Twitter. And next slide, please. And we also have our Oracle forums and Stack Overflow. In case you have any questions, you can definitely go ahead and post your questions there. Please use the tags for example, Oracle Forum, use Spatial, and for Stack Overflow, you can use Oracle Spatial, and we'll make sure that you get your answers for your questions. We also want to give a quick shout out to Dan and Albert, since they've helped. We've basically gotten the content to present from part of their presentations, as well as the spatial development and product management team. And Karine, I think we did have a couple of questions, but David went ahead and answered them. But we do have some questions asking for the scripts that you're using. So if there's any way that you could share those scripts, that would be awesome.
Yeah. I think I can publish those using a GitHub repository. So yeah, let me just check whether I have all the links to public resources mentioned. So and then you can find it in my GitHub repo.
Sounds good. Awesome. And I think we've covered everything for today's session then.
Okay.
I do think we do have our next session in October 31st. By the way, sorry everyone for the confusion of today's session's times. I know we had to make a change, but I'm very glad that you guys made it here. And yes, so definitely if you're interested on our next Ask Tom session, it's going to be on October 31st, since we have Oracle Cloud World coming up. I hope to see some of you guys there. But looking forward to our next session. I hope you've enjoyed this session today, and have a great day, everyone.